good morning/good afternoon. My name is Hide-Nori Kori from the Chiba Institute of Technology, Japan. Today, I will present our work entitled Load-Independent Class E Synchronous Rectifier with a Parallel Third Harmonic Resonant Network. Slide 2, Contents. Here is the outline of my presentation. First, I will give the introduction. Next, I will explain the problem addressed in this study. Then, I will present the proposal. After that, I will describe the design method. I will then show a design example. Finally, I will present the conclusions and future work. Slide 3, Introduction Background. Let's move on to the introduction. In recent years, power circuits that maintain high efficiency and stable output even under load variations have become important for high-frequency WPT systems and DC-DC converters. Here, WPT stands for wireless power transfer. However, conventional Class E rectifiers cannot simultaneously maintain ZVS and CV operation under load variations. Here, ZVS and CV stand for zero voltage switching and constant voltage. As a result, switching losses increase, the output voltage fluctuates, and additional control circuitry is required. Therefore, a rectifier topology that maintains ZVS and CV operation without complex control is highly desired. Slide 4, Introduction. Previous work. To address this requirement, a load-independent Class E synchronous rectifier was proposed. The proposed rectifier implements load-independent operation. In this topology, ZVS and CV operation are simultaneously maintained under load variations. In addition, this topology applies self-oscillation. Therefore, the need for external gate drive circuitry is eliminated, thereby reducing system complexity and cost. Consequently, miniaturization, high efficiency, and output stabilization can be achieved even under load variations without active control. Slide 5, Problem. Next, I will explain the problem. In the conventional load-independent Class E synchronous rectifier, excessive peak switch voltage is observed. This leads to limited power handling capacity and reduced device reliability. In addition, high-voltage switching devices are required. As a result, the cost increases, and on-resistance and conduction losses increase. Therefore, a new rectifier topology is required to suppress the peak switch voltage while maintaining ZVS/CV operation under load variations. Slide 6, Proposal. Next, I will explain the proposal. In this study, we propose a load-independent Class E synchronous rectifier with a parallel third harmonic resonant network. The circuit is shown here. In this circuit, L3 and C3 form a third harmonic resonant network. As highlighted in red, this resonant network is connected in parallel with the switch. As a result, the switch voltage waveform is reshaped by harmonic injection, thereby suppressing the voltage stress. The component values are determined using ASCO, a SPICE circuit optimizer, based on a differential evolution, or DE, algorithm to satisfy ZVS, CV, and self-oscillation conditions. Finally, the validity of the proposed circuit and design method is verified through simulation. Slide 7, Design Method Concept. Next, I will explain the design method. In conventional load-independent Class E topologies, the load-independent conditions are derived analytically. For example, in a load-independent Class E inverter, the conditions is expressed as phi equals pi over 2 minus pi d. Here, phi and d represent the initial phase of output current and off-duty ratio, respectively. However, in the proposed circuit, the insertion of the third harmonic resonant network increases circuit complexity. As a result, analytical derivation of load-independent conditions becomes difficult. Therefore, ASCO, which combines circuit simulation with the DE algorithm, is used. Circuit evaluation is performed using SPICE measurement functions. As a result, even without analytically deriving load-independent conditions, load-independent operation can be evaluated. For instance, the CV operation is defined as delta Vout equals the absolute value of VRL minus VRLN. Here, delta V represents the difference in output voltage. VRL is the output voltage at rated load, and VRLN is the output voltage at a varied load. Slide 8, Design Method Objective Function. I will now explain the objective function, or of. Measurement is performed using SPICE commands. Here, an example of SPICE measurement commands is shown. Now, please look at the waveforms on the right. As shown here, T_start corresponds to theta equals 0. T_rising corresponds to theta equals pi d. And T_stop corresponds to theta equals 2 pi. Using these timing points, the objective function is defined. In this example, ZVS is evaluated by measuring V_s at T_rising. The of for the proposed circuit consists of three components. First, the absolute value of V_s at pi d, which represents ZVS satisfaction, or the ZVS margin. This corresponds to the switch voltage at the turn-on instant, as indicated in the middle waveform. Second, delta V_out, defined as the absolute value of V_RL minus V_RLN. This represents the CV condition under load variations. It is the difference in output voltage between rated and varied loads, as shown in the lower waveform. Third, the absolute value of V_GS at 0 minus V_TH. This represents the self-oscillation condition. It corresponds to the gate source voltage relative to the threshold voltage at the start of a switching period, as indicated in the upper waveform. Slide 9, Design Method Differential Evolution. Next, I will briefly explain the DE algorithm in ASCO. First, the evolution of the parameter vector is described by this equation. Here, x1g, x2g, and x3g represent vectors of generation g. V is the mutant vector, and F is the scaling factor. Please look at the figure on the right. As shown here, x1g is combined with the scaled difference between x2g and x3g. This generates a new vector, which is used to generate vectors for the new generation. Next, the of is defined. The cost function is expressed as this equation. Here, W_obj is the weight for the objective, and W_con is the weight for the constraint. P_I represents the objective quantity, and P_j represents the constraint quantity. P_sj is the constraint limit. N is the number of objectives, and M is the number of constraints. Using this objective function, vectors are evaluated. Then, vectors with lower cost are selected from the parent and offspring. As a result, circuit parameters are optimized simultaneously to satisfy ZVS, CV, and self-oscillation conditions. Slide 10, Design Example Specifications. Now, let's look at the design example. This slide shows the studied system. As written here, an AC source is required. Therefore, a load-independent Class E inverter is used as the RF power source. Please look at this figure. On the left side, this part is the load-independent Class E inverter. In the center, the coupling coils are shown. And on the right side, this is the proposed load-independent Class E synchronous rectifier. Please look at the table on the lower left. The design specifications are given as follows. The operating frequency F is 1 MHz. The input voltage VIN is 10 V. The off-duty ratio D is 0.5. The rated load RL is 25 ohms. The harmonic filter order P is 3. The switch threshold voltage VTH is 3V. And the peak gate voltage VGS is 18V, x 1.1. Next, please look at the table on the lower right, which shows the coupling units measurements. The transmitting coil L is 21.8 microhenries. The receiving coil L0 is also 21.8 microhenries. The coupling coefficient K is 0.124. The ESR of L is 0.733 ohms. And the ESR of L0 is 0.726 ohms, x 2.1, x 2.2. These parameters are used in the design and optimization. Slide 11, Design Example Optimization Setup. Next, let us continue with the design example. First, please look at the waveforms on the left. These waveforms are partially shown for different loads, such as RL, 2RL, and 4RL. Here, the red circle indicates the important operating instant at equals. We evaluate the ZVS condition at this instant. Next, please look at the green box. This shows the operating conditions at each load. The conditions are defined by these equations. On the right side, the operation under load variations is evaluated using this equation. The desired operating conditions are formulated as above. Please look at the blue box. Here, P represents the objective quantities. These include the terms shown here. All of these quantities are minimized simultaneously in the of. Finally, optimization is performed to determine the component values so that all the desired operating conditions are satisfied simultaneously. Slide 12, Design Example Results. Next, I will explain the simulation results. First, please look at the table on the left. The results are shown for 3 load conditions, 25 ohms, 50 ohms, and 100 ohms. The average output voltage VO is maintained around 13 volts. This indicates CV operation under load variations. The peak switch voltage VSM is around 40 volts for all load conditions. The efficiency ETA is 89.5%, 87.5%, and 80.8% respectively. Next, please look at the waveform on the upper right. The output voltage VO is almost constant for different loads. As highlighted here, CV operation is achieved. Please look at the switch voltage waveforms. At equals, the switch voltage becomes 0. As indicated by the red circles, ZVS operation was achieved under load variations. Finally, please look at the waveform of VF. The waveform crosses the threshold voltage V_TH, and the maximum value satisfies VF max. This confirmed self-oscillation operation. Therefore, ZVS/CV operation and self-oscillation were achieved in simulation under load variations. The validity of the proposed circuit and design method was confirmed by the simulation results. Slide 13, Conclusions and Future Work. Finally, I will conclude this presentation. A load-independent Class E synchronous rectifier with a parallel third harmonic resonant network and a design method based on DE have been proposed. In addition, ZVS/CV operation, self-oscillation, and high efficiency were confirmed through simulation. As future work, experimental verification will be conducted to further validate the proposed circuit and design method. Additionally, the operating conditions will be elucidated through design curves and analysis. Slide 14, closing. That's all for my presentation. Thank you for your attention.